Okay, so I'm sharing an online link which where somebody has posted notes from the readings from this book. So what I want to, so like I said, we'll be starting with chapter 6 today, which is partitioning. But before we go there, I wanted to take a step back and quickly go over the major, discussion points we had over the past 5 chapters. Um, as we are seeing, like with every chapter that we are progressing, it's kind of getting more dense. So I thought it would be a good time to kind of spend 10-15 minutes to quickly breeze through the different ideas that we talked about. And if there are any questions where we really need, more discussions, I would encourage you to refer to one of our, recorded sessions for that topic, or we can also have an offline discussion. But in general, feel free to, jump in and highlight anything that I'm missing or anything that needs to be defined. All right, so the first chapter basically, so this book is essentially, we are in part 2 of the book, which is about distributed systems. The first part mainly focused on the general, the concepts around even single node systems. And I count the first chapter in this book, it's even more general, like, it's about talking about these fundamental ideas that we need in designing any data intensive applications, whether it's single node or distributed, regardless of that. So the author talked about these principles of reliability, scalability, and maintainability. And for me, the major takeaways from this chapter was um, to think about scalability, not just in terms of data volume, data scalability, but also resource scalability, right? So how does your application or scale when, you add a certain number of cores to your, system, or if you add extra memory, like what are the requirements of your application around that? So that was kind of the key takeaway for me in terms of scalability. The other thing was about measuring scalability, right? We tend to usually use this, general statistical measures of average, right? Average runtime is this much, average throughput is this. But this chapter also highlighted the importance of percentiles and also paying attention to outliers sometime. And they gave a particular example of Amazon, why even paying attention to outlier can be useful in some cases. So that was another thing. And the third thing that I got from this chapter was, if we also keep in mind, like I know, like in this broad group of SDE skills, some of us are also, looking into preparing for interviews. So what are the things that we can pick from this chapter that would be good for your system design interviews? And I think these principles are good to keep in mind whenever you are designing an application or a system there. So things like, how would you monitor your application, and read-write ratio, all those ideas. Those can be applied pretty much across the board. So good to keep in mind. So that was chapter 1. The second chapter on data models and query languages. This really touched upon, this was a chapter that actually offers you the high-level view on when it comes to choosing a database. So without knowing really a lot into how NoSQL, how, let's say, Cassandra stores data versus SQL Server stores data, you're not really going that deep in this chapter on that, but you are really looking at the data modeling characteristics, right? If I want to model connections, if my application is something which requires modeling connections, then graph model is a good choice. When do you choose relational model? What kind of relationships in your application are good for that? So those kinds of things. And then there was discussions around schema flexibility, schema, schema-based, schema-flexible databases. Third chapter was when we really started looking at things under the hood, how actually these databases that we talked about in chapter 2 we took some examples and we started looking into how they actually store data underneath. And there was discussions around, do you want to have an append-only storage or a mutable data store? What are the pros and cons of each, right? We did spend quite a bit of time on hash indexes, right? We know that when we maintain hashes in memory and memory is limited, then how do we make sure that we can make the best use, and how can we talk about sparse indexes? So I'm really, as you see here, I hope most of the terms that I'm mentioning are, familiar and you have a good understanding of them. But hopefully, if something piques your interest, my goal is also that to highlight the main key terms that we can go back and look at if we need to. The other things that this chapter touched upon was transactional versus analytical, right? And also column-oriented storage. So this chapter really was the first point of entry where we really did a deep dive, right? And the next chapter on encoding and evolution, the premise of this chapter was that the way you store your data in memory, so is different from how you store in file or over the network. So you go from pointers to a byte stream. And this chapter really talked about the different formats. How do you do this translation, right, of data from in-memory data structures to bytes? That is what we talked about in this chapter. And they discuss different protocols like thrift and protocol buffers and JSON, XML. So, but that was the, according to me, the key highlight there. Then the last chapter we talked about was replication, which was a lot of material there, right? You're talking about why you need replication, what are the different architectures. So does anyone want to quickly talk about, different architectures supported in replication? So I'm talking about more like single leader, multi-leader and leaderless. And in one of the Wednesday sessions we talked about how Google Docs enables collaborative editing. So in that, they talked about how they use multi-leader approach. There was discussion around concurrent writes. How do you handle that? Sloppy quorums, and it also touches upon CAP, like how sloppy quorum actually ties to CAP theorem as well. But yeah, I mean, like I said, this is a very I'm literally breezing through the topics just so that we don't lose sight of what we have covered so far. So, so that brings us to today's topic, which is on partitioning. So let me pull that. All right. So we know so anyone wants to kind of quickly go over the idea behind partitioning and what does it essentially offer us? I mean, it's kind of out there, but just to phrase it in your words and general. I mean, would be nice to have some interaction, right? Like, I don't know if I'm going too fast or.
Hi, Deepi, Nisha here. Can I go?
Yeah, sure.
Yeah, so essentially the idea of partitioning is, so for example, I want to store TBs of data, right? First thing is it cannot fit into one storage, right? So it has to be stored into multiple storage, right? Also the way we retrieve data, right? So we want to make it faster, right? So that's the general idea of partitioning, in the sense that we partition our data based on either rows or range or columns. There are different partitioning techniques. Hash partitioning is one of them. So we basically divide our data so that it would be stored in different partitions,
Right.
And these are logical partitions. So it could be on the same storage, it could be different storage. We don't need to bother about where it is.
Right.
Okay, so that's the general idea about partitioning.
Yeah, that's awesome. So yeah, I really liked how you touched upon logical partition, because we don't need to get carried away with, literally distributed. So yeah. So thanks, Nisha. So yeah, I mean, you want to spread the data if it can't fit into a single machine, and you want to split your query load, right? So any questions on that basic idea? Okay. So this chapter actually, even in the book, they kind of, so they partition that chapter as well in three parts. One is we want to talk about what are the different ways to partition your data. And the goal there would be, you don't really want to skew your data. So you don't want to have one partition with a lot of data versus another one having just a slice of it. And then you also want to make sure that when you query that data, not all your queries, what if all your queries are really hitting one partition? So you want to avoid that kind of scenario. And I mean, rather than saying avoid, how do you handle that kind of scenario? So the question that comes there is, which is the first part of this chapter, which is how do you actually, what are the different partitioning approaches and what are the pros and cons of that? So that is part number one. The second is, how do you handle partitioning when you also want to support secondary indexes? And I'll talk about a very interesting scenario that you can put in context. So that is point number two. The third is the idea of rebalancing partitions. So let's say you have 5 partitions of your database right now, and now you add more machines, or you have to take out some machines because some issues with that. So how do you actually rebalance your partition in that case? So these are the three parts of this chapter, and I hope to cover the first two today, depending on the discussions. Let's see how far we can go. Now, I talked about, I briefly mentioned that I want to present one scenario when I was reading through this chapter, and I was keeping that scenario in mind, and I was trying to map the different concepts that are talked about to that basic question. So that was really helping me to put things in context. So let's say you have a partition database. By that I mean, let's say you have actually physical partitions. You have, let's say, 5 nodes and your data is residing on them. Now you have some queries coming in, right? You have, let's say, a query which says, give me all the information where, let's say, is starting with A, right? A simple query like this. So this is the question, and how we can think about the different ideas around this, right? So to me, this was like my anchor, and I was trying to come back to it with every concept I discussed. So, and this can even be, in general, an interview question, because it's kind of a very high level requirement given to you. What are the kind of things you need to think about in this scenario? All right, so let's go further on this. So one of the things before starting with talking about partitioning approaches, one of the things that this author also mentioned was how partition is also very tied with the replication, right? So I'm not sharing that. You guys can see my Google Doc, right?
Oh, yes. Yes.
Okay. So author just wanted to, it was a good, just a, touch point about transitioning from chapter 5 to 6. So chapter 5 was about replication, but intuitively, right, if you think about it, let's say you have 4 nodes. How does partitioning basically connects with replication? So you have 4 nodes, forget about the followers right now. Imagine that on every node, your database is partitioned, and you have one partitioned on every node, right? So what would be the downside of that? Like, we have partitioned our database, right? So we can, it's not like all data on one machine, so that's good. And uh, and this picture, actually, he is showing this replication approach. First of all, can somebody tell me what kind of replication architecture is used here?
Yeah, single leader, right?
Single leader, right? So you have like one partition leader and then followers, and similarly leader for every partition and then followers, right? So that's a single leader approach. And what are the benefits that you see here?
You mean for the replication DB or?
Yeah, like in general, right? We had partitions plus replication here. So what are we getting by, having a partition database along with replication?
So I mean, in general, by partitioning, I feel like we get scalability
Mm-hmm.
because having everything on one partition or one node makes it like we cannot scale it, right? So if we partition it, we get the scalability. By replication, I mean, like in general, replication is like, should we call it like durability? Like if you lose one, you have some other place to
Right. So you
go.
have fault tolerance. Yeah, correct.
Durability.
Right. Can you elaborate on, so you touched upon this point of scalability for partition, just
Mm,
so that everyone is clear. So
right.
can you, do you want to elaborate on that, how we are getting scalability with
Yeah.
partition?
So the way we are handling scalability is like we divide the data in such a way that it's not completely on a single node.
Sure.
So if you have like 1 to 100
Right, right.
keys as the data, so we
Mhm.
divide it in like in three parts so that the
Mhm.
people requesting for the users requesting for some data goes to one node, and the requests are spread across different nodes so that
Right,
not one node is taking all the load. And
right.
that's the idea. How we
Yeah,
do that is something that I believe we will discuss. But
yeah,
that's the
right.
idea of like dividing the data in such a way that not a single node takes all the load.
Correct, exactly. So you don't. So there are two parts to it. What Naga said. So one is, let's say you have your data divided, and you don't even need to scan your whole data set, right? So you can just hit the right partition and get search through that data. The second is parallelizing your query load. So let's say you actually want to search all the data, right? You want to find, let's say you're storing employee data along with their salary information, and you actually want to find all the employees with salaries greater than 10K. Now, indeed, you want to search all the data. So you're going to hit, let's say, all the partitions, but it's not like only one node is doing the work, right? You are splitting your work across different nodes. And we'll talk about that approach more, but just intuitively, that's the idea there.
Ca- Can I add something?
Sure, sure.
Yeah, so I haven't gone through the chapter or such. I'm kind of behind, and it's the first time I'm attending this session. But looking at this diagram, I could see. So we are good on reads, right? We can spread the reads through all the
Exactly.
followers, and but
Yes,
write is a bottleneck here.
yes,
So
yes,
because it's only one leader, and write has to go through that, right? So
yes.
we, yeah.
Yeah, that's true. So this was like, like a limitation of single leader replication architecture.
Okay.
And this was like, in detail, we talked about that's where the multi-leader and actually leaderless replication comes in. But I think the main premise of this point was how partition and replication kind of go together. And they just highlighted it with one scenario. Yeah, but you're right. I mean, that's a good point to highlight that this is single leader. So the point is you are entertaining your rights on the leader, and then you are, synchronously or asynchronously, you can replicate it to the followers. And then you're supporting, basically your read scalability has improved because you can serve them from the followers. But if your leader goes down, then, or it becomes a bottleneck, that's an issue. So
We have partitioned the leaders as well, isn't it? I mean, the whole data set has been partitioned into the key
yes,
parts.
right.
So,
But,
yeah,
but
and that's why the thing is that in writes, we were always struggling in replication, even with multi-leader and leaderless also. We had so many issues, conflicts, and all those things. But that's the advantage of partitioning, that writes now become scalable. You don't have to deal with any of those issues which we deal in replication.
Okay, so
have
this
to
is
deal
a
with-
single leader, but we think about a single leader for a small subset of
right,
data.
exactly.
So, it's not really impact the whole thing, because if you
Right.
look at different nodes, you still see other leaders still, if let's say the leader on node 1 go down, right? And then you still have leader on node 2, 3,
Right,
or so
exactly.
they all can handle, different type of write and read. And then also on this one, I see that the other one is like the client, when they write the data, they read the data, they need to know, what's leader they have to write to.
Correct. Correct. Yeah, that's perfectly on. So this picture actually builds upon, depends on where you come from, right? If you're coming from replication, you are seeing this, that even though this is a single leader, but now we have added another layer of partition over it, right? So like Leon was explaining, even if partition 1 leader goes down, this model can still support, writes to some other, on some other data set, because other leaders are up. But we'll go deeper into it. The main point here was it solves some of the issues of having like completely unpartitioned data. So it helps us with some of the areas there. And when you combine replication with partition, that also actually goes back to helping us with fault tolerance and read scalability ideas.
Yeah. But I believe, like what Nisha was saying, there is no right bottleneck. I mean, like both are same. Actually, read and write had a similar.
No. So
bottleneck.
write has a bottleneck, right?
So there could be actually hot partitions, right? So we could have partitions where we are storing much more data than others. For example, some of the databases has limit on how big a partition could be. For example, Dynamo, it could be up to 10 GB. So automatically, if the data is becoming huge, they will actually create a partition themselves, right? So it would be like, even if you don't create it by using the correct partition key, they will do it for you. However, even if we talk about 10 GB of data, right, we could still have a bottleneck there because we are performing so many writes in that one partition rather than, that's what I was trying to say.
But read and write will have this similar bottleneck. Right?
No, but no,
Not
because
really.
not in this architecture, right? Like if you're a single leader, then your writes are always going to that partition leader. But your writes are scalable, right? If you have, let's say, I'm having 2 followers here and 1 leader. So my reads can be spread across these followers, but my writes for partition 1 are always going to the leader.
Mm-hmm. Okay.
Right.
Yep.
So yeah. Any other questions? But yeah, this was a good discussion. So kind of tying back that idea. So now moving on to the partitioning approaches, right? So I'm sure like a lot of us here would be familiar with these ideas, at least some of them. So, but let's kind of quickly, do it in an interactive way here. So this was an example. So let's start by talking about key-based partitioning, right? Let's say you have your data, you have 12 nodes, and you have your data, you want to store some words, English words from A to Z. Let's consider all uppercase or whatever, just 26 letters. So one idea is you put, you distribute it by 2 letters per, node. And because it's 26, let's say some nodes store 3. at the max. So what would be the downside of that? If I store AB here, CD here, and 2 letters per node.
I think like what Tisha was mentioning, like we might be writing.
Yeah.
No, not really. I don't think.
So here, some nodes may be overloaded, right? Like hotspots, like.
So generally we could have more names starting with say E or some letters, right? But some like T to Z would be very less.
Right.
So that would create something like hot partition, wherein in some partition we are storing a lot of data, but in some partition we are storing very less amount of data.
So yeah, so the point is you shouldn't just go by your key, range. You should also, like the author says, adapt to the data, right? So yeah, so you captured it right, Nisha. So we have to look at what is the distribution, whether your data is evenly spaced within that key range. So that is one. Now let's say, so they gave this, style that, okay, we understand that we will have to adapt our partitions to data. So this was the way that they gave, right? So we know that towards the end, like these letters Z and T and all this range won't have, let's say if your data is not, you don't have as much data in here. So you combine these, letters in one partition, and whereas A to B is a much higher data set. So that's the idea. Now, let's say we go with this refined partition based approach, and how can you make your search? Let's say you hit a certain partition, first partition. Now, how can you make your searches faster within this partition?
Again, make them sorted.
Yeah, right. So in general, if you just dump your data, like that, you just store it in a random order, you have to do a linear search, right? But to further optimize it, you can keep it in sorted way, and then you can use a binary search, and you can even build indexes on the top of it.
Yeah, and also we can do range-based search. Like if there is any range
Right.
search. Yeah.
Yeah, that's good. Yeah, I think that was also.
I think that's what he was discussing in the book. Yeah.
Yeah. There was another limitation they mentioned about, right. So the other thing that they mentioned about was we should also be cognizant about. So we talked about right now the data distribution, right? Then another example is, I think initially Nisha or Naga, one of you mentioned about this as well. So this is talking about the query pattern. Let's say you are partitioning your data by key timestamp now, and you have one partition per day. So when you are actually writing data to your database, you are really hitting one partition at the time of write during a particular day, right? So that is another thing to keep in mind about your data load or write patterns. How do you maintain your partitions accordingly? So we talked about two key things in the key-based partition. One is to be careful about how to have an efficient partition that can support good writes, like write rate. And the second is, once all the writes are done, your database is, let's say at a given snapshot, you have all your data. How do you make sure, not a given snapshot, I would say at any given time, you should try to avoid the skew in terms of data in your partitions. So that was another. Now this leads us to the second partitioning approach, which is partition by hash key, right? So what we are doing is, this is something that we are all very familiar with. You have a key, or let's say a name to store. You actually apply some hash function, and then whatever value you get, you actually define partitions based on that hash value, and then you dump your data there, right? So what they highlight is that while this seems like a good idea, but the challenge here is that if you're trying to search by, okay, I want all the data between A to C, right? You can't just directly do that range query, because now you have used this hashing mechanism by which, even let's say you are talking about all the names with A, they might be scattered across different partitions based on what their hash value is. So that is one. And then they gave an example of how Cassandra handles it, right? And here's the idea of having compound keys. So what they do is they actually keep a first part of the key that is used to determine the hash, and then the rest of the columns can be used for searching through within that bucket. So that is how Cassandra handles it. The key point here is that don't think of your partitioning only based on a single attribute or single key, but actually think about even the possibility of having compound keys. So that was interesting.
One limitation, I don't know if they mentioned, but the key generation, right? So if you're looking at huge data, is there a risk of having the collisions on the keys?
Yeah, definitely, right? Like with the hashing concept in general, you can have, it comes back to, I think, the idea of having a, how good is your hash function, right? And even if collisions occur, right, then you are going to maintain, let's say, a linked list, or you're going to have, let's say, a binary search tree, within that bucket. How do you keep your data? And according to me, that is where really this idea comes in, that once you hit a partition, how do you efficiently search within it? I won't, in my mind, I won't think of like you can have an absolute hash function, which is like no collisions, right? Because if your, let's say number of nodes is smaller than the key size, then of course you're going to have collisions. But the bigger question is, when you have collisions, what can you do to actually still make your queries efficient? Does that make sense?
Yeah, yeah. And that's never an overhead, right? Like creating these hashes, handling collisions, and like rehashing.
It's it's why in what way, like what do you mean by overhead?
I'm saying like, is that an overhead? Like, would it cause any?
I see it as a trade-off, right? I see it as a trade-off. Let's say when you call something an overhead, right? The question to me is, okay, can I avoid that completely, or is there another approach that allows me to totally avoid that? And let's say a better one. To me, I believe
That is a trade-off instead of.
Yeah, like that's the trade-off, right? How do you try your best to actually have a good hash function, and then keeping in mind that when collisions occur, what can you do? As an example, right, it's a little segue to this, but let's say you have a hash, this hash base scheme, and you have n number of buckets. Now, when collisions occur, I actually already talked about it, but just to clarify, that collision occurs in a single bucket. Let's say you have 10 items. So what would be the time complexity there for searching something within that bucket?
10 items. We have 10 items, and
yeah, like let's say you have collisions and you land up with, let's say, X number of items in a single bucket, right? Want to now query comes in where you actually, based on the hash of that key, you end up in that partition which has X keys mapped to it. So
simple best case would be like O of X, because you have to,
right,
yeah, but
right, because you have to search through that thing.
Yeah.
But can you further optimize it?
I don't think so, because it's all like different keys, right?
Right.
I could see like it could go worse depending on the collisions. It could go, we don't know how far it could go.
Sure, like that's why we said like X items, right? It can be like
Yeah. For X
whatever.
items,
So like binary search tree, right? Yeah, log X. Yeah.
you mean like ordering the hash keys and doing binary search? Yeah.
Right. So something like that, right? Rather than having a linked list where you just have to traverse it, like you're saying now, the order of X. So I think some people mentioned this. So we can have actually, let's say, a binary search tree, or how can we store them in a sorted order, maintain a sorted linked list, so that we can do some binary search, right? That would reduce it to order of login. Right. So the point here is not to go into deep into data structure there, but the point is you're having a hash-based partitioning. You are not totally discounting the fact that collisions can't occur, because that's not practical, right? When collisions occur, you do. And the question then steers to, okay, how can we efficiently search when a bucket contains multiple items? And that's where some of these ideas come into picture.
And I mean, like maybe this is little off the topic, but can this are these hashes generally used to also see like if replication is done? I mean, like once we have this hash.
So what do you mean replication is done?
I mean, like we have a leader and a follower, right? So if you want to know what the follower is, updates.
Are you asking like, are you asking like if, let's say, replication is there and when a read query comes in, right? You want to map, you want to have your hash such that it goes to a follower, right? Not a leader. And whereas if a write query comes in, you always want to hit the leader of that, if it's a leader-based approach. I believe so. There would be possibly, two hash functions, one to support read queries, one to support writes. If we are following a single leader or a multi-leader approach.
And this hash is only on the key, right? We already have a key and we hash only the key, not the complete data. Okay.
Yes, right. Yeah.
Okay. Sure. Thanks. I was thinking else.
No, these are good questions. Actually, just wrapping our head around what we have talked in the previous chapter discussion. So the other thing that in line with what we were talking about, right? How your data is scattered and what are the challenges in this hash key based partitioning. They also gave an example that, all right, so you have a compound key, right? So now you're hashing by user ID. And once you land into the right partition, if you are keeping data sorted by timestamp, then you can do a range query based on that, right? Give me all the updates made by the user between this interval to that interval, right? So you first hit the right bucket by using user ID, and then you do a range query on this. So this was another example which really highlights the value of compound keys.
Is there a way that I can find in the range, but like I say, I want to find the last 10 posts. Doesn't matter from which user posted, but
yeah, so in that case, so that's a good question, right? So Leon is asking, okay, I don't care about the user. I want to know what are the last 10 updates that were made, right? In that case, so let's open it for people, right? What do you think? Would this kind of, partition key help?
No. Because it's based on the user, right? User ID first.
Right. So, what do you think? Like, what should we do? So everybody understands, right? This scheme won't really help because we care about the last 10 updates by the timestamp. We are not bothered about the user. Any ideas on that?
So you can make the timestamp as your partition key and then maybe user ID as a sort key.
That's one idea, right? So if we know our query pattern is something where we are always, querying by this kind of pattern, then of course switching your, stuff is one idea. What can be the other way? Let's say you already have your data partition by this approach, right? Suddenly a new query comes in, something like what Leon said. You don't want to just totally, deconstruct your data and repartition, right? So how?
Then, yeah, then you should create secondary indexes in that case.
Exactly. So yeah, I mean, it's like you're creating an additional index that can support a new class of queries that you're seeing in your work.
So what that secondary index look like?
Right. So we'll talk about that, but very quickly, if I were to give an overview. So secondary index is something that, so what do you think, first of all, like even forget about partitioning, right? What do you think is idea of let's say a secondary index in databases? I think that will help us to, and it's like open for everyone. So not to put anyone on spot, but how do you get
I thought in this case, the update timestamp is the secondary index and user ID is the primary index.
That is, well, right now, it is not really, you can call it a secondary index, but I'm thinking one step more, right? If you're, Leon, like you're saying, if user ID is a primary index, right? So you actually, if you keep it this way, then you have to hit all the partitions because you really don't care about your user, right? And then you have to pull, let's say, last 10 updates of every user, and then you have to combine the results, right? To find a global, last 10 updates. Does that make sense?
Yeah, so essentially it would involve scanning the entire table to find out the last 10 updates.
Right. It's more like scanning the whole table, and then it's more like a scatter gather approach that you are, really hitting everything, getting your local data, and then combining it further. But what the idea of secondary index, another way to look at secondary index is you want to avoid all this work. So let's say you actually also, I'm trying to think of a clear example. You kind of, a secondary index idea is you don't want to search by user ID. Now you want to directly hit the 10 timestamp. So how can you actually store your data in another way? Is there?
So, but are we saying we are using the timestamp directly, or like are we saying we'll make a hash out of this timestamp and username?
Well, you can't really make. So the question I have is, if your data is already partitioned by user ID, right? You already have your data in buckets. What do you? How can we hash it based on timestamp now?
I mean, I don't think we will. I don't know. Using timestamp has its own limitations, right?
No. So either what you can do is, like if you don't have your data, let's say you have your data with you, you haven't partitioned it. In that case, what Leon is saying is, if I know that my queries are going to be like, based on timestamps, then yes, I should hash them based on this. I should make this a primary key. I should make this a primary key. But my question was more like, once I have decided a primary, hash key, and then later I hit a new query pattern, right?
Right.
Now I want, okay, I want to find data by timestamps, right? So this scheme as such won't help. Like, Nisha was explaining, you have to actually hit all the partitions and then combine data. But the other way is, if you have storage, right? Another way is you can actually create another partitioning scheme where you're having your data hashed by timestamp. So when your query comes in, depending on, but it's in general, it's kind of a storage footprint, right? You're storing some data redundantly. So that's the downside. But yeah.
So generally, the way we would partition DB data in DB is based on the query patterns, right? Based on all the type of queries we are sending, we should partition as per that. And if just by having a table, it cannot satisfy all the queries. Like in this case, if we are querying with the timestamp, it will not satisfy that. So in that case, we actually need to create indexes, secondary indexes, so that we can satisfy those kind of queries faster. Okay, faster, and obviously cost will also reduce. So
No, so that's true, Nisha. So one question I had there was, I know I have worked on this from relational point of view, but not from distributed. So from that perspective, my understanding of secondary is it's like an additional, like you said, secondary index, right? It's an additional index we are maintaining to
actually, yes. So generally, storage cost is less. Okay, and we also have an option of projecting only the columns we need. So it's like, let's say
no, that's true. So that's true. Like when you talk about indexes, I understand that in general, the storage footprint compared to the whole table is less because, like you said, it's less columns, you know, and stuff like that. But my question is more about adding any additional indexes to your database will add extra storage, will require extra storage for that index space.
Correct.
Yeah.
I think we.
But the way, sorry.
Yeah. Okay. One quick thing, actually. I think, Nisha, from what you said, deciding on the user scenarios first to come up with the keys is like more of a NoSQL kind of way, right?
No,
But
it's not about NoSQL.
database, it's not really true because you can always.
Yeah, like any DB which supports this kind of structure, it could apply to any of those.
Yeah, like it has nothing to do with NoSQL, right? Even in relational, it's about you have a database. And that actually goes back to one of the things that Nisha earlier pointed. Let's not think of partitioning only from a physical distributed fashion, right? For example, I work on single node systems where we have, you know, terabytes of storage, terabytes of even memory, right? And we are even having, you know, these terabytes of data. And we are using column store indexes. And how do you actually define partitions, even like logical partitions per se, even within single node? And even it's a relational database, so you have to define your partitions based on what's your query pattern. Am I querying on timestamp? Am I querying on user ID? It still holds true in any partitioning idea. I don't say that it's tied to NoSQL and SQL.
It is not tied, but I think it's easier to think if somebody's has worked on NoSQL. It's actually easier to think because these techniques map very clearly to NoSQL. But yes, as you said, it doesn't really apply there, but it's easier to think from that perspective.
Right.
When we discussed last time about B-tree trees, the index stays in the tree, but the data file has everything appended sequentially at the end. So if you just need last end, don't go through the index. Just pick up the last few kilobytes of the data and get it.
Right, but here we are talking about actually, I think the question was coming more from if your data, so you are assuming that you have an index, right, which is actually pointing to a sort of, which is a pointer to some data on disk, right? Now, our question was coming more from what if your index is built on, let's say, user ID, whereas you are trying to look for, so even in your example, right? If I have an index on user ID, I hit that partition. If I pick the last 10 rows, that's only going to tell me the last 10 of that user ID. But I want the global user ID, global last 10 values, like updates based on timestamp. So I have.
I mean, just take the last few rows from each partition and then just combine.
No, exactly. So that is one idea, right? That's a scatter gather, but you're hitting all the partitions there. But we were trying to think of an approach where.
I mean, hitting a partition is not a cost, right? You're just reading the last 10 rows from the data file. You're not scanning the whole partition or not scanning the.
No, but what about like if you think about when you're having this, data spread across different nodes, right? So compare it with the scenario where you have your partition based on timestamp, right? And I only want to find data based on certain time interval. I don't even need to hit these different nodes across different regions in my database.
I mean, partitioning on a timestamp is a really bad idea, right? How
No,
granular
that
you
is
want to go?
sure. I mean, I think we are kind of maybe mixing different scenarios, right? There are downsides to partitioning by timestamp because there are like,
I think a better example could be, say, employee ID and department ID, right? Obviously, you can create your data on department ID, right? And I'm not sure who was asking the question, but you cannot really fetch last 10 records without going to each partition, because the way you are reaching to the partition is through hash only. So there is no way you can retrieve directly from file. It is not possible.
What I'm saying is each partition generally, I mean, I'm talking about the RDBMS perspective. Each partition is basically has its own table space and index space. So each partition will have its own file. And what I'm saying is, let's say we have 10 partitions. The optimizer may just go after all those 10 partitions and just pick up the last chunk of the data and then just merge it.
And that is fine.
Yeah, but still you are going to those 10 files, right? Those are 10 different partitions. And when you're doing that, at least I can tell you in terms of AWS, you would be incurring network cost, okay? More network cost, more read units. So there is something called read units and write units, which comes into picture. I don't know if book talks about that, but you would be paying more.
And there is no that's true. And there is, in partitioning, we always have to keep in mind, like there is no partitioning scheme which can satisfy every, if your query pattern is very diverse, you can't really have best, optimized way for every single query. You have to come up with an efficient partitioning which satisfy most of your workload. So there might be trade-offs you have to make. So I think it's like almost like just 3 minutes short of the next session. So I think this is a nice segue to our next session, and we can pick it up from there. So we can
just to add to what I was saying, like so I was talking about, one was cost, right, in terms of read unit and write units. Another is obviously your query retrieval will be slow because you are going into 10 different partitions, right? It is essentially as good as scanning entire table, all the records. So how would you find out last 10 records, right? You would have to scan entire table. Only then you would get those records back, and that will take a lot of read units, and those involve
and
more
also
cost.
in general the cost, and also in general the cost of combining results, right? You got 10 from each, now you have to further sift through them. But yeah, so these are the kind of things I think we should think about when you're brainstorming partitioning approaches and stuff. So
so in generally in NoSQL, you try to denormalize the data. I mean, so one scheme might not serve all the types of queries you want and paths. So generally in a DynamoDB or Cassandra, you try to create one type of table for every query that you'll serve. Since it is a LSM based one, the write will be fast, but every query that you need to will be a read. You will be doing it at a particular table itself, or generally, so you can have secondary index or global index. It depends on that. So I mean, not all of them support global indexing, but DynamoDB or something, you have global indexing as well. So you either add a global index, or you can add the second, I mean, you add another table which has this corresponding secondary index.
Yeah, so DynamoDB has something called local secondary index and global secondary index. In local secondary index, you cannot have a different partition key. So it will have a same partition key, but a different sort key. You would have a different sort key. But global secondary index can have a different partition key and sort key. So it all depends upon your query pattern. That's the first thing you need to know before you even think about designing it.
All right, guys, great ideas, but I would have to hold this discussion. But yeah, so I think let's close this on the point that we have to look at query patterns, no global, partitioning that satisfies all of them. So let me stop recording.